All right, welcome back. Let's start today's lecture. So before I start it, I just want, because I've seen some questions regarding the lab 1 on the forum. So I just want to emphasize one thing one time again. So the feedback system will give you some error messages. For example, if it says WA, basically it means wrong answer, or it will tell you if your program cannot be executed correctly. By executed correctly, I mean it will stop somewhere and cannot output anything. Or it is possible in some of the labs and project. In some of the labs, it will tell you that your output format is incorrect. All right. So all this information is the best we can do. The rest is for you to figure it out. And the feedback system is not designed to offer you debug information. It is designed to tell you if you've got the marks that you feel satisfied. Something like that, right? So you can't do debugging totally rely on the feedback of the system. That's the point I want to make here. So the question such as why I got a WA for this particular question, we cannot answer that either on the forum or in person, unless we review your code and tell you the reason, which we cannot do that because that is unfair to other students, and it is impossible for us to do the same thing for all the students. So in order to maintain the fairness, we cannot answer such kind of questions. On the other hand, I do encourage you to discuss on the forum and share the test cases if you would like. Okay. So basically, the correct way of doing this whole labs and projects is that you design your own test cases, and you use your test cases to test if your code is correct or not. Just like what you will do in your real job. But let's say in this course, we do allow you to share the test cases on the forum, such that you probably can help others, or others may occasionally, your test case is not fully correct, so others could point that out for you as well. So rather than ask why I've got a WA here, or why my code cannot be executed, you should get used, either design your own test cases or make use of test cases posted by others. Try to improve your implementation. So that's the right way of doing this project, doing this labs, and doing the project later. All right. So that's what I want to clarify before the lecture starts. All right. So let's go back to the data warehousing. Yesterday we have introduced why and what is data warehousing. Hopefully you can still remember that. If you are not, you can review the video again. Now today we're going to see how we're going to discuss this multi-dimensional model, which can be seen as a logical level of how we do this data warehousing. And during this today's lecture, I want you to keep these two questions always in your mind. try to think about it. One is that why this kind of multi-dimensional model can help data warehouse, or how it can help data warehouse. Or say, given a specific data warehouse application or data warehousing task, how do you complete the task with the help of this kind of multi-dimensional model or data cube, right? That's the first question. The second question would be, what's the difference between this multi-dimensional model and traditional and the things that you've been familiar with in traditional relational database? So please keep these two questions in your mind while let's go through this multi-dimensional model thing. Right. So basically, data warehouse is based on a multi-dimensional data model, which views data in the form of a data cube. So what is a data cube? It is a multi-dimensional generalization of a 2D spreadsheet. All right, so we will give the detail about this multi-dimensional model or the data cube, but let's give you some intuitive idea about what it would look like. Okay, so since we say it is a multi-dimensional generalization of a 2D spreadsheet, so a 2D spreadsheet would be something like this, right? You all have, I believe all of you have used Excel or similar applications at some time. So this is a 2D spreadsheet. Okay, it has so 2D for dimension, right? Okay, we will discuss these terms or concepts later, but a multi-dimensional generalization is to generalize 2D to multi-dimension, to generalize 2-dimension to multi-dimension. Well, we cannot, it is pretty hard for a normal person like me, or probably you, to imagine what a 4D space looks like. So let's try to generalize it to 3D, so you would have an idea, right? So for a 3D, it looks pretty much like this. Pretty much like this. And in the 2D spreadsheet, each cell is like this, okay? But in 3D, it is generalized to because each cell is a 2D square or something. But in 3D, it is a cube here, a small cube here, right? So this whole thing is also like this is a cube, right? When you put the data in it, it is a data cube. I mean, this is not the official definition, but hopefully it will give you some idea. I mean, this kind of things is what we're going to discuss and deal with in today's lecture, probably also lecture of next week. All right. So a data warehouse is a data cube to some extent. Now let's look at some key concepts. So basically, there are two key concepts here in order to define or describe a data warehouse. One is facts, the other is hierarchies. So first of all, what are the facts? Right? So facts are typically transactions in this course. Well, you could see some other types, including, for example, snapshots. If you look at if you read the textbook by Jiawei Han, so those transactions, if you still remember, it's like, for example, again, the example at the very beginning of yesterday's lecture. So the finance group have got a bill to pay, right? After they pay the bill, they record this transaction into the system. So that transaction is a fact, right? But if you remember, that transaction includes many information. For example, what is the account name, the total number of the total money, of course. What is this bill for, right? And maybe what's the location of the for example, it's an electrical bill, so which building is this bill belongs to, or something like that. So these are the description of the transactions. All right. Now, if we split these descriptions into two types, one is measure, the other is dimension. So the measure is the numbers that can be aggregated. For example, the total money is numbers and can be aggregated. And also it is meaningful to aggregate it because, say, I've paid 3 bills in this week, right? If we add the numbers together, I will know the total number that I've paid this week. So the numbers can be aggregated. We call it measures. That's one type. The other type, sorry, I haven't finished about measures here. Yeah. All right. So account name. Account numbers. Are they numbers? They are numbers. Can they be aggregated? Well, perhaps not, or at least it is meaningless to aggregate the account numbers, right? Let me see. For example, the time step, the dates, for example, they are numbers and they can be aggregated, I guess, but still, I mean, it is meaningless. So we need to choose carefully about the measure. So usually the measure is the numbers that can be aggregated. If there are multiple numbers that can be aggregated, let me see if I can find a good example here. Alright, so for example, you buy something, or you buy a dinner. You would pay for actually the money you've paid belongs to two parts. One is GST, and the other part is excluding GST, right? So which one shall we do the aggregation or takes as measures? It depends on the application, or depends on the end user, or the one who make the decisions using the data warehouse. So here, the measures could be all of them. See, GST and the part without GST could be one of them. Or this GST example is not very good because GST is always 10%. But I guess you know what I mean. I mean, if you have multiple choices, you need to decide which one is the measure, and this is based on the needs or the requirement of the end users or the decision makers. Okay, you can use multiple measures in one data cube, which we will I think we will touch that later, or you can use take just one of them in your data cube. So that's for the measures. For the dimensions, it's the context of the measure. If you still remember, in that transaction, we have, say, this bill belongs to, say, NSW department. So that is a dimension. This dimension maybe called location. So it could be NSW, could be Victoria, could be Queensland, so on and so forth. And the time, of course, the time is one of the dimension. It could be in the first week of 2021. It could be the bill could be paid on let's say 25th of February, right? Also the type of the bill, it is a water bill or it is an electronic bill. These kind of things which describe the transactions or are the context of the measure are the dimensions. So here the goals for dimension modeling is try to surround facts with as much relevant context as possible, or say as many dimensions as possible. Why? Because or later we would see some more concrete examples, but here just to give you an idea, right? So it just like consider yourself as a as a manager, right? You want to see so usually you want to see every aspect of the data, right? You probably want to know like the bills have been paid for different departments or at different time period, right? Or for different categories, for example. So this kind of dimension modeling gives you different ways to do the aggregation of the measures and give you different ways to view the numbers, right? And also, I mean, it would make the queries easier because the more relevant, the more dimensions you have, the queries can be more flexible and lower chance to. It is possible that some queries you cannot answer it if you don't have enough dimensions, if you don't model this thing properly. So that's basically the idea here. So that's about the facts, which is also the most important part in a data cube. Right, now hierarchies. So hierarchies provide a context of different granularity, right? So hierarchies is because, as you see, context here. So hierarchies is to describe the dimensions. Right? For example, if the dimensions is more like, for example, the time. So we take time as a dimension. But for a specific transaction, the time is a specific date. For example, if we ignore the hours and minutes, so it is a specific date. But so what is hierarchies? So hierarchies is that, all right, so for time we have different granularities. We have a year, which year it is, quarter, right? Month, and perhaps weeks, and then the day. Right? So as you can see, I mean, these different granularities actually can help the data cube provide more specific information according to the demands of the end user. For example, sometimes the end user would like to see, just want to see the total number of the cost in 1 year, right? Then you will need the granularity to be year. But sometimes the end user want to see the curve or want to see the change of the cost along with different months. In that case, I mean, the granularity should be months. So that is what hierarchies for. All right, so always remember we have these two concepts, the facts and the hierarchies. And then we will see how do we model these things and make them as a data cube like this. Like this. All right, now let's look at one more concrete example. Because we need to first model this whole things, and then we will see how a data cube would looks like. Right? So we have the, say if the data comes from a supermarket, or you can think of it like comes from a supermarket group like a Woolworth or Coles, right? So basically, the subject is to analyze the total sales and profits. The total sales and profits. Right. So as you may know, I mean the profits actually equals to sales minus cost. Okay. Now, what is the fact? What's the fact? So the fact is each sales transaction, right? You go to the supermarket, you buy something, then you pay what you buy, then you take the items with you, go back home. For the supermarket, it will record this kind of transaction. All right. So what are the measures in this transaction? You would have dollars sold. This is what the customer, the total number that the customer pays, right? The amount sold, how many items does the customer buy? Cost is the money that the supermarket used to buy this item, to buy these goods, and then to sold to others. So these are the measures, or say more like raw measures. You can directly get them from a database or from the transaction itself. And there is also a calculated measure, which is the profit here, because we need to use the total sales, which is the dollars sold, minus cost for the items this customer buys. Then we can have the profit for this transaction, right? So as you can see, you would have different measures, and which measures to use depends on what kind of application you want, or what kind of data the end user want to see, right? So these are the facts. What are the dimensions? So you still remember we need to have for facts we have measures and dimensions. Sorry, and then after we have dimensions, we can decide what is the hierarchies. Right? So for fact we have measures already. So what about dimensions? For each transaction, right? There are several contexts to describe this transaction. For example, the store, right? Where you buy these things, which store. So this is one dimension. The product, like which product do you buy? Of course, you would buy multiple products. Yeah. So they probably belong to different, different categories of products. But think of, if you are the owner of the supermarket, you would really like to see which kind of products, or which specific product have the best sales or whatever, right? So that's another dimension. Time is important, of course. I mean, it could from a specific time within a day to say the year, up to the year. It depends on the hierarchy, right? And also, I mean, besides that, these dimensions, we can also have other dimensions. For example, the customer information, right? for the customer, for example, like, you know, there are two categories at least. I mean, those who have membership card, or those who haven't or have not used their membership card, right? And also for those who have a membership card, I mean, of course, the supermarket can have its ID, so it can be a finer granularity for this customer as well. All right. So with the dimensions, after the dimensions has been decided, we need to decide the hierarchies, right? For example, for store, it's like the location of the store. So the hierarchies could be from state, which is the highest level, if you like, right? And then down to council, right? To suburb, or sometimes you could use a postcode as the, you know, to describe the store. But the problem of using postcode, at least in Australia, in NSW, one postcode may belongs to may include multiple suburbs, actually, and it may even cross councils for one postcode. It is possible, right? So, well, these are the designing issues, which we will touch it later. But the reason that I mention this here, because just want to show you that there are multiple ways. Okay, there are multiple ways to make your hierarchy, and again, it depends on the application, or depends on the needs of the end users. Always remember that, right? For product, we can have, for example, its brand, right? Its category. Between that, I mean, for example, a bread, it could be made by wholemeal, right? There could be some fruit in the bread. So all these kind of things. Of course, the brand of the bread, and also the category, because the bread should belongs to food. Right. On the other hand, you probably have other things belongs to different categories. So that's product. Time, we have mentioned that before. Customers as well. So basically, you would have different dimensions that you're going to use to model this data, and you need to decide the hierarchies of the dimensions. So now let's see, how do we visualize the cubes? Right, just like what we always do, I mean, we start from an easy case, then we see how do we extend it to a more complex situation or condition, right? So for the easy case, I mean, the data cube, if we only take 2 dimensions, which are the product, wait a minute. Okay, which are the product, and the city is actually the store or the location. Okay. So if we only have 2 dimensions, which are the city and product, and the measures are the total number of the total say sold dollars. Okay. Then, as you can see, I mean, here you would have so this column, the columns, this dimension represents the product. Okay, so there are 4 types of products P1, P2, P3, and P4. And for the location, we have 4 different locations. They are the cities. So it's so the example is from the textbook is in America, so it should be New York, LA, and so on and so forth. So what does this cell mean? This cell, the 454, means the total sales of P1, of product P1 in New York City is 454. All right. So this number, how do we get this number? It comes from one or more transactions. All right. So that's the idea. So this is a cell, and that's why we say the fact is those non-empty cells. Because if you remember, the fact are those transactions. If this cell is empty, means no transactions here, right? So no fact here. So we have sales, fact, measure. We have so measure is the total sales. Dimensions are the product and city, right? So that is a simple example. I guess every one of you can easily understand it, but I want to say a little bit more about this. Say the difference between this kind of data cube, even it is a 2D data cube, the difference between the data cube and the tables in a relational database is that you can actually change rows and columns. You can consider like you can change the rows into the columns and change the columns to the rows. You need to rotate this this table to a right angle, but again, I mean, all these numbers still make sense, and it actually affects nothing about your procedure of the processing of the queries. Right. And if you remember, this is quite different from what you do in relational database. Because in relational database, the rows and columns has their specific meaning, right? So every row means a transaction or an entity, and every column are the attributes. Right? Each column represents one attribute. Therefore, it's kind of weird if you turn it around. And furthermore, I mean, let's consider a normal implementation of a relational database. You can think of if you really change or swap the rows and the columns, when you want to insert a new record, you can't easily do that anymore, if you think about that, because every insertion is on the row level. Right? So this makes the tables in traditional relational database quite different from the data cubes here, because here there's nothing special about rows versus columns. Right? That's the thing. All right. Now the question is, how do we generalize it to 3D? Right. For example, we want to have another dimension called time. Right. Of course, I mean, we can still do it in a 2D table or cube if you like. For example, if we want to add time, another dimension called time, we can still do it in a 2D cube, where we probably, let me see, we probably need to do it no, like this. So we would say if the time is in the quarters level, right? So we add we nested the time dimension under the product, right? For example, this is Q1, the Q2, Q3, Q4, and so on and so forth. Of course, all the cells here would be divided into 4, represents hosts. So in this case, this cell means the total sales of product 1 in the first quarter in New York City, right? And this is the product 1 in New York City in second quarter. So you can still do that, but think about what if you further generalize it into a 4-dimension or even higher dimension, then the table will become less and less intuitive, right? You can still do that, but it will become less and less intuitive, and also more difficult to handle. Therefore, we will generalize it in a way like this. So the 3D cube and hierarchies. See, for this 3D cube, we would have 3 dimensions, right? D for dimension. So we have this dimension is a city, right? This dimension is product, and this one is month. We will look at the hierarchies later, but so there are 3 dimensions now, and for this cube, this cube, this one, actually it requires you to have a little bit imagination about this 3D space, but I guess all of you should have this ability. So basically, you can think of this cube, this small or this small cell in this cube. It represents, say, the sales of book 176, because on the product dimension it's book 176, right? In New York, because in the city dimension, here is New York. In January is from here, can be found in this cell. All right, in this cell. And then you can have you can do the similar thing. I mean, for each and every cells here in this cube, they have their own representations, right, of this measure. So it's all about measures and dimensions. Now let's look at the hierarchies. So basically, we have 3 dimensions here: product, location, and time. For each dimension, they have different hierarchies. It's kind of like a tree of dimension values. A tree of dimension values. For example, for product, we have the product, which is the finest granularity, and the category is a coarser granularity, and this all is a default level, if we call it each of them as a level. So all is default value. All means default level. All means all the categories. Okay, it's like the aggregation of all the products, no matter which category are they, right? Well, you may ask, like, okay, this hierarchy actually assume that one product should belong to one category, right? But it is actually possible that one product can belong to 2 categories. For example, a movie can belong to action movie and a comedy movie at the same time, right? or even more categories. So in a data warehouse, this is not a very good way to model things. It makes things more complex, right? So we won't touch this in this course, but if you are interested, I mean, you should be able to find the relevant method or the relevant concepts in the textbook. Okay, so we always assume that a product belongs to one category. All right, and also here for the location as well. I mean, there are store level. If store has an ID, it's kind of the finest granularity. Then city, then state, then country, then region, and all. It's easy to understand, right? For the time here, we have day, we have month, we have quarter, year, and all. We can also have week here, but you need to choose either one of the two paths. Okay, it depends on your application again. This is because you can see there is no relation between, no clear relation between weeks and months, right? Because 1 week can across multiple months, so you cannot put a week here. You cannot do that, or you cannot put a week here. So basically, you either choose all year, quarter, month, and day, or you choose all year, week, and day. That's the thing. All right. So here, always remember when we draw these kind of hierarchies, we use the lowest level for the finest granularity, right? And for the highest level, it should be always the default level all, right? And the granularity is become more and more coarser from lowest level to highest level. That's the thing. I mean, later in your homework or in the exam, when you draw this kind of hierarchies, you need to follow this kind of rule. Okay. Well, just to clarify, we haven't put the numbers in each and every cell, but you can imagine there are really numbers here. Okay, there are really numbers here. So the numbers could be, number of items sold or total number of dollars that sold, or the cost. I mean, depends on, again, the need of the end user, right? So a little bit more about hierarchies. Before it's like a abstract way of represent a hierarchy structure. So basically, here is the left part is more concrete. It's more concrete. So basically, you would have, say, book. The O is the default level, and because we're talking about products. Okay, so we would have food, beverage, book, and maybe some other categories. And for book, for example, it has different sub-levels or sub-items, where one of them is book 176 is the one that we have mentioned before, right? So this is a hierarchy structure. It's more like a tree of dimension values. A tree of dimension values. So the first level is the default value or default level or. So from the second value level is all about dimension values. Depends on different granularity, right? And here on the right side, we do have even for one dimension, we could have multiple design of hierarchies, right? Here is a an example, and I guess, yeah, here is another for the time dimension. You could have different design. Well, for the time, I mean, which design will be used totally depends on the needs of the end user. But here, these two design, the main difference is the granularity, okay, or the number of levels. So for the left one, it only has 3 levels. For the right one, it has 5 levels. So which one is better, right? So in general, we would like more levels, because more levels gives you the final control of the granularity. Also, it gives you gives the data warehouse or gives the data cube more power to answer different queries with different granularities, or gives the chance of the end user to ask for different questions or queries, right? And also, I mean, this kind of design, although the number of levels becomes more, that means the complexity of the data cube becomes more, right? Or the data cube becomes more complex, no, right? So we usually choose to use a design with more levels, as more levels as better. All right, so we will have a break, and we will come back later.